Okay, well, I'm Ville. Thanks for having me here today. So I'm currently working as a principal engineer at Adroll. So, and like Raish mentioned, we are producing tons of data, which makes it very interesting. I've been actually doing big data with Python for like too long time, probably at least since 2000. And maybe something that should be interesting to you is that if you ever find yourself in the need of MapReduce and you like Python, as obviously you do since you are here, you should go to discoproject.org, which is Disco MapReduce, an implementation of MapReduce that uses Erlang and Python that has been around since 2008. I started the project, and the community is really pretty active, and it's really great if you like Python. Well, but this talk is not about that. This talk is about something else. This talk is about the stuff that I and Adroll have been working on like for the past couple of months. Especially related to the question that I'm sure that many of you, and actually like the previous speakers also have clearly had, which is that when a kind of a modern company like Adroll, or pretty much like Eventbrite, I'm sure, or any other company producing tons of data has, that when you want to understand what's going on in your business, you want to do business intelligence, and today it involves data and lots of data. So really the first question is that how do you actually slice and dice, how do you query tens of billions of data points or hundreds of billions of data points? And now, if you have been following the field, you know that there have been like tons of interesting projects that have come out like for the past, during the past 5 years, say. So there are like interesting projects that work on top of Hadoop. So there is of course Hive, and there's Peak, and well, I mean, you might use something like HBase even, or of course, of the newer crop, you have things like Impala. But I mean, it's very much like an ongoing thing. So I mean, there isn't really a clear winner in that space. And in a way, I do believe that it's very hard to have a one project that would fit in all problems. But still, it's a very valid question. And actually, the reason why I'm here today and why I think that like this stuff should be interesting to you is that actually we ended up building a custom in-house solution instead of using, well, maybe a proprietary solution like Vertica or Redshift or one of the well-known open source projects well, let's say Hive. And well, the thing is that our solution that we have built over actually the last couple of months, of course, based on much of the previous work that we have done, is implemented in Python. And now, if you, of course, if you think about Python, is that everybody knows that Python is a slow language. Slow meaning that it's nowhere near the speed or performance of C or C++ or Java even. So in a way, I mean, you might think that especially when you are interested in doing low latency processing in Python with huge amounts of data, it's totally not a match. It's totally an oxymoron statement that you are saying that you are doing big data processing in Python and it's low latency. Of course, the thing is that if you don't care about latency, you can do MapReduce. And then, well, I mean, then it's totally doable as proven by Disco, for instance. But the interesting thing here is that we are definitely interested in kind of keeping things at low latency. And the reason for that is that we want to support first ad hoc querying. So I mean, you don't have to define the queries that you are interested in beforehand. And secondly, data exploration as well as data science, really kind of doing the iterations really fast. And you shouldn't have to wait for hours for a MapReduce job to finish. So the question is that how do we actually do this with billions and tens of billions of events so that you can get results in seconds? And well, now the thing is that, of course, if you had like tons of machines at your disposal, which is very easy nowadays, in a way, I mean, like doing distributed computing is very easy. I mean, especially if you have immutable data. Of course, if you do have mutable data, then it actually gets horribly, horribly complicated. But if you have immutable data, you can just have a like shared nothing architecture. You just shard your data, have as many machines as you need, and things are kind of, they do work, but I mean, it adds an extra layer of complexity. And it adds also, of course, like all kinds of issues with cost and complexity and so forth. And especially when you are starting to do more complicated advanced things like data science, you really want to keep things simple. So as a kind of interesting kind of a starting point motivation for the whole thing about Python and Python being slow, here's a small benchmark. So, I mean, this is a very small, of course, like a subset of data. I mean, it's not small in the absolute sense still. I mean, 1.5 billion rows in your database is a pretty sizable database. But I mean, like, that's a kind of amount of data we are probably producing in an hour or so. So the size of the data set is about a little bit more than half a terabyte, so not that much. Obviously, in our benchmark, we really care about latency, so smaller execution time is better. We chose the fastest result from 10 consecutive runs, meaning that, well, I mean, like if there happens to be just one bad query for some reason, we don't count that. And we don't, of course, cache the results. So this is really about like testing the querying performance. Well, now the thing is that we are comparing our system in this motivational example to Amazon Redshift. And I guess we'll actually mention about Redshift in the last talk. So unless you have heard about Redshift, it's a data warehouse offering by Amazon, meaning that it's basically a data warehouse as a service. So if you have ever used Amazon services, so you know that it's very easy to get started with these things. So you just click a button and you have your own data warehouse up and running. Well, in this case, like I mentioned, I mean, like this is not about distributed computing. That would be a separate talk. I mean, this kind of, in many ways, I mean, that's kind of, I mean, there are really many good solutions for that. This is about asking how much we can actually do with a single machine. So look, I mean, we are taking a single server. That's actually the most powerful server that you can find in Amazon with 244 gigabytes of memory, 16 cores. And so it's pretty much a monster machine. So it's really a pretty decent iron. And we pick a comparable cluster in Redshift. So we take 3 nodes, unfortunately, since kind of otherwise it wouldn't work. And actually, in this case, Redshift is getting twice the number of cores, but about the same amount of RAM. And well, so it happens that actually Redshift, if you run it in this configuration, it would end up being a little bit costlier. But I mean, maybe that's not the consideration. And now, of course, if you wonder if actually Redshift is a bad apple, so it's just a crappy system that we decided to compare against, at least some people claim that it's faster than Hive. I don't have personal experience, but like you can actually read the blog articles and believe them if you like. Well, now the thing is that looking at the actual numbers, since this is all about analytics, so I should have made it maybe more clear that in contrast to maybe, let's say, Elasticsearch, which is really great for heterogeneous data and structured data and so forth. This is really about like having numerical data, having tons of numerical data, and having large aggregations over numerical data, and not so much about looking up single rows in a database like what you would do with a NoSQL database or key value database, say. So in this case, we are taking probably the simplest aggregation that you can imagine. You are summing over a column in a table. And remember that, again, we have about 1.5 billion rows, so you are basically summing over 1.5 billion values. So it's a non-trivial thing, but as you can see, both Redshift and our system kind of manage that pretty well. And yes, our system is faster, but I mean, the difference isn't that huge. One thing to note here is that, of course, both the systems scale pretty much linearly. So imagine that if you had 10 times more data, 15 billion data points, Redshift would most likely take something like 19 seconds, and our system would take 6 seconds. So it's not an order of magnitude difference, but it actually might make a difference when you're actually doing your interactive analysis. Another example, a typical thing that you might want to do is that you take an aggregation and you want to group that by a dimension. Dimension might be a country, it might be a customer ID, or something of that kind. Again, I mean, the systems are pretty much comparable, and again, you might consider that it's pretty amazing that something written in Python is as fast as pretty much state-of-the-art distributed database that's really kind of written by people who should know what they're doing, and I'm sure that they do. Well, actually, things start getting more interesting when you start taking aggregations over a number of columns. So here we are taking an aggregation, the same summing over 7 columns, and now suddenly our system is 5 times faster than Redshift. So you can kind of guess the pattern. Actually, if you fast forward this to 250 columns, you can see that Amazon starts taking 8 minutes, whereas our system is pretty much the same as before. And now, of course, you might say that, well, it's a pretty kind of a bad example. I mean, no one ever wants to do an aggregation over 250 columns. Well, except if you do data mining or data science or anything of that kind that actually, let's say, it requires you to kind of take all the features of a certain kind, and then you want to see the results. So it's actually a pretty realistic example, and this was one of the motivating reasons why we started considering alternatives to Redshift. Since, of course, as you can imagine, this only gets worse when you get more data. So, again, this is a Python-based system. I mean, it should be totally impossible to have anything like this. So, I mean, it's a single server. It's 1.5 billion data points, and it's outperforming the best of the breed system running on 3 servers, having twice the number of cores. Well, actually, it's a real system. It does exist, and the stack looks pretty much like this. So I know that I don't have too much time, so unfortunately, I don't go into detail here. So this is pretty much an overview talk. I'm pretty happy to kind of give you any details you might be interested in after the talk. But I just want to highlight these 3 items here. And so basically, just to give you an idea how it works, I mean, typically analysts or anyone actually wanting to do the interactive analysis or data exploration actually would use a tool like Excel or Tableau, which is a visual business intelligence tool, to actually generate SQL queries that then hit Postgres, that then actually hit this thing called Multicore that I'll be talking about soon. Then it hits our servers, then it goes to these worker processes that we have one per core, and then it goes to this thing called Numba, more about that later, and then to LLVM, and then to our specially encoded data. And that's pretty much the process how it works. And I want to highlight these things there, I mean, starting from bottom up, since I think that's the interesting part. Well, really the thing and the secret sauce here, and the reason why it is actually possible to do this with Python is that we do care about data structures. So the thing is that actually kind of caring about the language that you are using, in a way, yes, you can get like really order of magnitude improvements, let's say 10 times faster if you use C instead of Python. But the thing is that you can get infinite improvements if you actually rethink the algorithms and if you rethink the data structures that you are using. So let me just give you a kind of a quick idea what I'm talking about. So here, that's really the data that we are talking about. So it's events. I mean, I'm sure that like all of you have seen something like this. So it's basic like JSON messages. The data is produced by our system, so it's very homogeneous. We know the fields that it contains, and they all have the same form, basically. And like you see, I mean, like we have some Boolean fields, some strings, some integers, all nice and simple. Now, of course, well, again, I mean, we have 1.5 billion of these rows in the benchmark. Well, I mean, since it's very homogeneous data, what you can do is that you can, of course, drop the keys, you can drop the field names, and again, it's the same data, nothing changes. It's a very trivial transformation. Well, I mean, what you can do as well is that, of course, if this is just JSON, it's most likely strings, maybe sitting somewhere on your disk waiting to be decoded as JSON, so that's not very nice. What you can do instead is that you can actually encode everything as integers. So again, I mean, like here, so true and false could be zeros and ones, obviously. Countries can be encoded with integers between, let's say, 0 and 300, like you give an integer to each country. The cost could be, again, another integer, obviously. So you get this like a nice matrix of integers. So it's a 3-by-3 matrix. And now, well, the thing is that computers actually do like matrices. So matrices are really, really nice in computers' point of view. And, well, the thing is that that's, of course, this very small matrix. Actually, if you now think that we have 1.5 billion of those rows, it looks more something like this, and this is not 1.5 billion, this is something like 200, but you get the idea. It's just kind of the same idea. We have lots of integers, but instead of having a one big solid red matrix, it's sparse, it's spotty red, meaning that actually we don't have values for all possible rows, so it becomes a sparse matrix. And that's a very good starting point. And there I have that's pretty much kind of the 100% of the original size. So the question is that can we actually make this more efficient, since still this matrix is actually pretty huge. So if you just took all your data and encoded as integer binary data and had it as a sparse huge matrix, still, I mean, processing that would take quite a while. Well, the first thing that you can do is that you can recognize the fact that different columns have different types. So this is, of course, the basic observation that all columnar databases probably did already in 1980s. That, well, I mean, some of the columns might be strings. Some of them might be, like we had Boolean flags. So obviously, you can encode a Boolean flag as a bit instead of, well, let's say integer. And let's say that like you have a cost value that I had in the example, and the cost varies between 0 and 1 million. So, well, then you can just use 3 bytes or a 24-bit integer to encode that value. So again, I mean, you get huge, huge savings. Like already just by doing this, you get like 50% smaller matrix than what you started with. So it's a big improvement. And this is, of course, something that all columnar databases do, including Redshift. So that's really the basic trick. Well, still, I mean, the question is, can you do something more? Well, the matrix looks pretty random. So, I mean, like kind of it's not obvious that what you can do with a random matrix. But the thing is that actually when you sort the matrix, I mean, like patterns start to emerge. So it's not like a random matrix after all. But when you actually sort the rows, you start seeing that, well, I mean, for one, I mean, there are like all kinds of things that you see happening. And always when you see things like that, you might start thinking that, well, I mean, maybe there's a way how we can actually leverage this information. And that's really the case. You can actually, and note, by the way, that this is exactly the same matrix. We just sorted the rows, so it's the same size and the same information. And all these transformations are lossless, so I mean, we are not losing any data. But I mean, one obvious thing that we can do is that we can get rid of duplicate rows. So we can just kind of squeeze the matrix and then get rid of like redundant data. So obviously, if you have 3 rows that have exactly the same values, and then they have count 1, you can just represent them as 1 row and say that the count is 3. And now when you are summing over these things, you are summing over 1 row instead of 3 rows, but the result is exactly the same. And again, I mean, the matrix is much, much smaller. So that's really a nice like way to kind of compress the stuff that we're working on. Well, there's at least one more thing that we can do. Actually, there are like tons of things that we can do, but I mean, this is just to kind of give you an idea of the process. Well, I mean, one is that what I mentioned about different types, yes, I mean, it's a good idea what like all these systems do, that you use different types for different columns, but still there's the question that if you use, let's say, the 3-byte column that I mentioned, and you have a value of 1, and you are still using 3 bytes to encode value of 1, which is like really redundant, since I mean you really don't need 3 bytes for that. So actually what you can do is that you can devise some encoding, variable length encoding, so that you use the minimal number of bits to encode these values. And now so it happens that if you look at the result is very kind of a way smaller than what we started with. Actually it's just a 15% of the original size, and it's all very compactly encoded, and like you have minimized the redundancy in the matrix. And why this is important? Well, I mean, there are a number of reasons. One is that, well, overall there's less redundancy, so there's just like fewer computations that you need to perform. So I mean, like I mentioned, I mean, you want to get rid of duplicate results that just result to unnecessary work being done. But maybe the most important point is that like dense matrices or any dense data is very cache efficient. So you know how CPUs work. So when you do summing, let's say the CPU knows that I need to sum over some column, it goes to RAM, it fetches the item from RAM, it maybe goes to L2 cache that's near the CPU, it goes to L1 cache, and then it does the computation, it fetches the next number, and if it so happens that the number is already in the cache, you don't have to go to the RAM, and actually you can do probably like 1,000 times more work just by using the data that's in the cache than what it would take if you actually needed to go to RAM. So you really, really want to pay close attention to cache efficiency of your data if you are operating at this level. And well, I mean, one interesting feature of this is that also when you are kind of getting rid of redundancy, you are kind of implicitly building indices, but that's maybe a topic for another talk. Let me focus on the cache efficiency, since that's actually brings us to the next topic, which is NumPy. Well, so it happens that if you care about something as low level as CPU cache efficiency, of course, using a language like high-level language like Python is a bit problematic, since there's lots of many things happening behind the scenes and behind your back. So there's garbage collection, and of course Python, the CPython virtual machine, of course, does all kinds of things. So it's very hard to, of course, make sure that you are not doing unnecessary work. Well, so it happens in the Python world, there are like really lots of and many interesting projects going on today that help you to produce really efficient code in Python. NumPy is one of those projects, so you should definitely check it out. So what it actually does is that as it says, it's a just-in-time specializing compiler which compiles annotated Python and NumPy code to LLVM, and LLVM being the compiler toolkit developed by Apple and others. And how it works is that like it can take any Python function, like an example here, you just add a decorator, like which is in this case called autocheat, and it magically compiles your Python function to machine code. And it's super, super magical. Think about it. So you have a Python function, and you just add a decorator, and suddenly you have this super high efficient version of the function. So it's great. Well, now the downside of that is that unfortunately it's not able to take any arbitrary Python code and make it fast. So it mainly works with numerical code. So if you ever are using NumPy or things like that, it can actually automatically detect the types of matrices that you are using, and using that information, it can actually produce efficient code. Whereas if you are doing like what we are doing 80%, 90% of the time with Python, doing string manipulation and stuff, it's actually not that good. But I mean, so it happens that this is actually exactly what we need. We need a way to produce low-level code that manipulates numerical data. So NumPy is a good match for the project. How NumPy actually works in our case, and this is the reason why the talk is titled Metaprogramming, is that we are actually generating code, Python code, on the fly. So again, going back to the stack, you remember that at the very top of the stack, we have a tool like Excel or Tableau or maybe Analyst typing SQL. So what happens is the SQL query actually goes to Postgres, and the Postgres, through a number of steps, actually sends the query to our system, and eventually it hits the part of our system that handles the compilation. The compiler actually dissects the query, takes the columns that you are interested in, and takes the where clauses that you are interested in. And basically, knowing the matrices and the types of matrices we are analyzing, and knowing the query, it can actually generate a piece of Python function that answers exactly the question that you are asking. So this is actually the kind of, you get the idea what do the kind of the Python, the automatically generated Python look like, and it's very low level. And the reason that it's low level is that that's exactly the type of Python stuff that NumPy likes. So now we can actually feed this automatically generated Python function to NumPy, which compiles it to LLVM. So this is the LLVM intermediate representation. So it looks like assembly. So if you have ever done any low-level coding, it's very low level. But the thing about this is that when you are operating at this level, it really gives you an opportunity to kind of optimize things like cache efficiency. And of course, the thing is that now, I mean, we are actually producing a piece of code that's it's basically specialized for the type of the query and for the kind of the data that we are operating on, which is another key to efficiency that we are seeing. So that's how it works. Well, the last step is, I don't know if you can see that, but it says that like the last step is to compile this to optimized machine code on the fly. So another interesting kind of side effect of this is that we can leverage LLVM's optimization framework to actually optimize the query that we are executing. So if it so happens that there are any kind of redundancies in the code itself, LLVM hopefully can take care of that. So that's really super awesome, and that's also a key why we can both combine the densely encoded matrices with densely optimized code and get the result that you saw earlier. Well, now, let me actually check the time. So, okay, I'm almost practically running out of time. Let me just fast forward. So, the thing is that, like I mentioned, no system is an island. The analysts actually want to use this. Analysts like SQL, as we heard in the previous presentation. So we want to provide a SQL interface. Now, of course, we are not as insane as that we would be thinking that we can actually implement the SQL standard by ourselves. And knowing that there are really excellent projects around, like Postgres, I mean, of course, we do want to leverage the whatever is available. And now, of course, there's the question that how do you actually use something like Postgres or any relational database with like a NoSQL custom system that we built. Well, now let me introduce you to Multicorn. So again, if you have never heard about Multicorn, actually I hadn't, so I mean you should definitely check it out. Yet another thing that like you should be using. It's a way how you can actually map your any Python data source. Yeah, I know I should be. Well, anyway, let me just fast forward. I know we are running out of time. Anyway, the point is that you can write things in Python and they will show up as normal tables in your Postgres database. So you can actually do all kinds of joins, all the magic in SQL, while actually offloading the big data stuff to the whatever backend you might be using and the deliverable in our case. Well, let me just quickly conclude my talk. Yes, is this cheating? Yes, and that's exactly the point. What do you want to do with a language like Python is that you want to embed all the domain knowledge that you have and all the tricks, all the kind of the information about the constraints that you know that, well, we will never need queries like this, and you want to implement the system that really takes that into account. And the key thing here is that you can actually outperform any system built in any language when you just design your data structures correctly, even if you are using Python. And actually, it might be that, especially when you are using Python, since many of these things that I showed here would have been such that, yes, they are possible to implement in C, but I mean, it would have been extremely painful to do all those transformations and stuff in C, which is which is quite not as expressive as Python. So you can actually benefit from the fact that Python is really expressive and do things that would be way too complicated to implement in a low-level language, and actually you can beat a low-level language in their own game in this way. So thank you. So actually we are using Erlang, by the way. So. Let me see if I can. Okay. I think I'm confused. Is bit of the software I can use now? Does it have dependencies on NumPy? Oh yeah, well, unfortunately, so it happens that I actually haven't asked my boss yet if we can open source this, so no, it's not yet available. What I hope that what's the kind of the take-home message here is that you should definitely check out NumPy, you should check out Multicorn, and you should also always have the feeling that anything is possible with Python. So, I mean, if anyone tries to tell you that it's not fast enough, I mean, they are wrong. I mean, like, it's really not the case. But yes, it does require some work. Do you see a possible implementation of Blaze for multiple data type optimization? Well, if I remember correctly, Blaze is actually another project by Continuum.io, which is behind Numba, and they have like a very similar worldview, how you can actually efficiently encode matrices and perform fast computation on matrices. And I'm definitely looking forward to whatever they end up doing. So it just so happens that this was something that we needed now, and well, I mean, and Blaze is not yet available, at least not the features that we would need. Oh, that's an excellent question, yeah. So the question was that, like, how much of the performance difference between Redshift and Electron can be attributed to the fact that actually our system is running on a single machine, whereas Redshift is running on multiple machines. So obviously there's some like a network overhead. So, well, I mean, one thing is that, especially when it comes to kind of a basic summing over columns, of course, actually how Redshift works is that it offloads like computation to these individual shards, and the shards just like return whatever like intermediate results. So there should be very little like a network communication happening between the nodes. And actually there's a dashboard in Redshift that shows you the network communication, and it's really pretty minimal. So I don't believe that that's the reason. It's really, well, okay, maybe I shouldn't elaborate. Okay, go ahead. Yeah. Yes, so multi-core. That's a very good question. Of course, the whole point behind this thing is that, well, I mean, we definitely want to be doing and like utilizing all the cores that we have on the machine. It's very CPU intensive thing. So I mean, yes, you do want to use all the CPU power. Well, I mean, like really the obvious thing with multi-core is that you have, so you have K nodes, K cores on your system, so you have K processes. So I mean, you have one process, one worker process per core. Well, I mean, the things are practically not quite as simple. What you do want to do as well is that there's this thing in Linux that you can actually set the task affinity so that the kernel won't be like a moving process around, especially with a machine like ours, which is actually a non-uniform memory access machine. So you want to kind of pay attention to things like that. But yes, the basic approach is to have well, I mean, like in this case, 16 Python processes running on the machine. Right, so that's another good question about everything that I presented here today is about reading. It's kind of everything is about reading, and there's nothing about writing. And well, I mean, I like Erlang. I'm a big fan of immutability, so I mean, I don't typically change anything, and especially the historical data doesn't change. So unfortunately, well, I mean, maybe fortunately, I'm like working in the field of analytics, which is like mainly the part that actually gets all the crap that the guys end up producing on the operational side, and of course, like kind of people who use the systems. So my worldview is that I mean, we are actually using Kafka as well. So what happens is that Kafka basically pushes and produces a tons of data, but I mean, of course, after we have collected those log files, they don't change. So it's all immutable. I don't have to care about writes at all. So that's very easy and simple. So. Okay, thank you.